if I got it. Oh, you got it. You got it. All right, cool. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you again for these students. Just ask you to bless our work today, help us to understand a little bit more about differentiation and the gradient and everything. And we just thank you again, Lord, for your many blessings. In your name I pray, Lord Jesus. Amen. All right, so it is usually the case, it's often the case in here that I have time to answer homework questions or give you hints about homework, stuff like that. You just have to ask, you know. So like I told you guys in announcements, have one more day, all right? So do you guys have any questions about the homework in particular? What's that? No, I said that you guys had one more day. Yeah. I did make an announcement in Canvas, right?
Yes.
Okay. Yeah. I'm not saying that to like provoke you. I'm saying it because I honestly am not entirely certain that I made the announcement. So, yes, sir.
So on 34, it's asking you to take the limit x of y.
Yeah.
And then it gives you like the x minus 1 quantity squared times y squared divided by x cubed y cubed.
Right.
Times x minus 1. It's just like, because you can't change it into polar coordinates. So like how, do you just plug in A and B?
Well, if you change it to polar coordinates, that really only gives you insight. If we're talking about standard polar coordinates, that would only give you insight at the origin. So AB here is an arbitrary point. So the question that's being asked is, how does this limit work out at any point in the xy plane? So A comma B equal to 0, 0 is one case, and your polar coordinate substitution would answer that probably. I mean, I can tell you this much, you can cancel the x minus 1 over x minus 1, right? So you can do that. Another hint, x cubed plus y cubed factors into x plus y times x squared minus xy plus y squared. So this limit suffers a divergence along the line y equals minus x. All those points have to be dealt with separately. You can also prove that the quadratic there has no zeros. So essentially the only place where you can have a divergent limit is along the line y equals minus x. So your analysis is going to have to split between those cases where a is equal to minus b and where it's not. It's a hard problem. There's a lot to talk about here. Other questions? Yeah.
This might low-key be a dumb question.
Probably not. Which problem?
But number 42, I'm just not sure. Like I don't remember, and I couldn't find in my notes. What is the limit-based definition?
Oh, sure. Yes. So if we, here you go, definition. If we have f is a mapping, say, from R2 to R, right? Then partial f, partial x. And I think I asked the point AB in that problem, is that right? Which is kind of annoying. Or no, I didn't. All right. Sorry, I'm bouncing off a conversation I had with a student the other day. Let me not do that. So if we calculate this partial derivative at the point x naught, y naught, what's the deal? Well, that's defined to be the directional derivative at x in the x hat direction of big F at the point, right? But that problem asks you to use the limit-based definition, right? So the limit-based definition is simply this one. The limit as h goes to 0 of f of x naught plus h, comma y naught, minus f of x naught, y naught, divided by h. And likewise, partial f, partial y at the point x naught, y naught. Well, how's that? The limit-based definition of that partial derivative is simply this. Limit as h goes to 0, f of x naught, y naught plus h. So you're varying the y component, but not the x component. Like that. And I think this particular problem is actually solved in the end of chapter problems. If you go hunting through there, you can see how I wrote it out. And we did one or two of these. One of those we did in class also. But yeah, it's a good question though. Because you might wonder, what in the world do I mean by limit-based definition? So that's a totally legitimate question. Yeah, that's what I meant. Other questions? So there's two things that I've missed, I think, so far in our discussion of partial differentiation. One of those is the definition of critical point, right? So we've talked a little bit, well, actually we've talked a fair amount about the gradient, right? So, what was our definition? Nabla f is equal to partial f, partial x, partial f, partial y, right? For f, a function on R2, right? And what did we do with this? We had a few different things, right? We had the directional derivative in the u hat direction of f at the point P was the gradient of f at the point P, right? Dot product with the u hat vector. We pointed out that that's equal to the magnitude of the gradient of the function at the point times the cosine of the angle between, the direction in which we're ascertaining the change and the gradient vector. Now, of course, that presumes that the gradient vector is non-zero, right? So we can calculate the directional derivative in this way. I mean, this formula actually still makes sense even when the gradient's zero. But so as we discussed, this basically describes the rate of change of the function at the point, right? It can be at most the magnitude of the gradient, and the smallest, most negative rate of change possible would be, the minus the magnitude of the gradient, right? If we go along the line perpendicular to the gradient, right, the tangent line to the curve in question, if we think about f of xy equals to a constant, that level curve, then if we want to stay on that level infinitesimally, we would just follow the tangent line to the curve, which is also perpendicular to the gradient, right, which would be along the normal line. If we studied this further, we'd come to an understanding that if you look at the, z equals f of xy, okay, well, let me not get into that. That's enough. All right, so then there's a special case, right? So this is just a quick review of the things we've talked about. But if we have that the gradient of f at the point P is equal to 0, then P is a critical point. And I suppose that we'd also, in Calculus 1, what was our definition of critical point? Do you guys remember? Yeah, it's either undefined or 0, right? So we'd also throw that in here. If you have a multivariate function where one or more of the derivatives, the partial derivatives, don't exist at the point, then that would also be a critical point, right? Basically, funny stuff can happen there. As we're, like our larger, the larger question we're going to start asking and answering over the next week is, how do we maximize or minimize a function of several variables, right? That's an interesting question that we're gonna tackle head on. And these critical points are going to be a central part of that story, right? Because these critical points are going to end up being places where we could perhaps have a local maximum or a local minimum, right? Now, of course, this is the two-dimensional definition. What's the more generally, if you have f going from Rn to R, a function from n variables to a real valued function of n variables, then, of course, the gradient of f, it's an n vector, right? It's an n vector. It's a vector field in n dimensions. And if the gradient of f at the point P is equal to 0, then P is a critical point. And again, we'd also, don't make me write it out, but it is also true that if one or more of the partial derivatives was not defined at the point, we would also consider that to be a critical point of this function of n variables. All right? So, example, if we looked at f of x comma y equals to 10 minus x squared minus y squared, calculate the gradient of that thing, what do we get? What's the gradient of f here? I heard minus 2x, right?
Yep.
Minus 2y. Are there any critical points? Right? Yeah, gradient of f equal to 0, 0. So we need both the x and the y components to be 0. So of course 0 is minus 2x, 0 is minus 2y. I really didn't need to write this much. So clearly 0, 0 is the critical point. But, you know, generally speaking, this could be more challenging, right? But before I do that, we can graph this one, yeah? What is this? So this is one of these deals, right? I'll put the y-axis and the x-axis down here just for means of, you know, illustration. What's this point? Like f, this point right here in the graph of f, that point would be 0, 0, what? 10, right? And pretty clearly that's a local maximum, right? That's also where the critical point is in the domain. Right? And then it just keeps going down and down, right? So in fact, not only is that a local maximum, that's a global maximum for this function of two variables. Right? Next week, we'll look at like analogs of the first and the second derivative test for functions of several variables, but we're not there yet. Yeah.
If you're done with this, can you explain what a level curve of a gradient, or what a level curve is?
What is a level curve? Yeah, we can talk about that again. So for this one, what's a level curve? So given a level function on xy, on the xy plane R2, right? If we have f of x comma y equals to a constant, the solution set of this is a level curve. So level curve is just another name for an equation. All right, but we're being systematic. You know, the solution set to an equation is, you know, you should have talked about graphs of equations in like your pre-calculus, right? There's a difference between a graph of an equation and a graph of a function. Level curve is the systematization of the graph of an equation. We're giving a name to the equation, f, right? And what we've shown is that the gradient of f, which of course is partial f, partial x, partial f, partial y, right? What we showed the other day was that if we looked at this curve, right, and we take a particular point on that curve, right, then the gradient vector field points perpendicular to the curve like this. Right, those are is that, yeah?
In the homework, it has, I think the equation is a function of the plane or something, and then the level curves are just straight lines.
The
Problem 40.
Yeah, so there the function's x minus y, yeah.
So it's,
But that's in two variables, so that's not a plane. X minus y equal to a constant is in 2 dimensions, x minus y equal to a constant is a what? Yeah, it's a curve, but it's a line, right? Yeah.
so is it incorrect to understand it as, is there any relation between it, if you put that in 3D?
Oh, I wouldn't do that. I wouldn't try to put that in 3D. I don't think that's helpful. We need to be able to think 2-dimensionally for that problem. Because once we go to 3 dimensions, then we're talking about a level surface, and then the gradient is still normal to the surface, but as a 3-dimensional vector. I mean, we could make a correspondence between these two things, but I think it would just serve to confuse the class if I did that. So I'll resist the temptation. But I could talk to you about that in office hours if you wanted. But, yeah. So like, here's a, similarly, if I had, say, f of x comma y equals to mx minus y, equals to b, this would be a level curve, depending on what I make m and, choose whatever m you want, that would be a level curve, right? What is that level curve? This is, another way of looking at y equals mx. Oh man, I was supposed to put a minus here. Oops. Plus b, right? So I would be recasting the mx plus b line as a level curve, the level minus b curve. And if I calculate the gradient of f, what do I get? I get m minus 1, right? And if I was to plot the level curves here, right, slope m, right, b, you have different choices of b, of course. Where does, like if I, there are, of course, infinitely many choices, but we can draw a vector that's tangent to these lines, right? Like if I do like this, my bad. Aw, man, well, come off. Oh well. If I did like this right here, right? If I go 1 over, how many do I go up? I didn't say m was equal to 1. Oh, sorry. 1, what? What did you say?
You go over 1, you go up.
Yes, up m, right? So this is change in y over change in x along the lines, right? So I'd go up m. 1m would be a vector that points along the lines, the level curve. That would be a tangent vector to the level curve. And of course, the gradient of f is m minus 1, which is what? Perpendicular. Yeah, this had to happen by the general calculus we worked out like the other day. All right, not an accident.
Would it be pointing away from
It's pointing that way because it points towards the, wait a minute, minus b, the other way. My bad, that was that minus b business. See, as b what? As b increases, we're going down in levels. So this is the direction in which minus b increases. I should have made the level b work out to a positive, then we would be less confused about this at the moment. But anyway, yeah.
So is the gradient having relation to a normal vector?
The gradient is the normal vector to the curve. So if my curve is like this is my level curve, right? If I take a particular point there, the gradient will point perpendicular to that.
So the normal vector is normal in relation to two vectors, but this is in relation to a curve.
Right. Yeah, it's a normal line. The tangent to that, this tangent line You know, we could parameterize that if we had a parameterization of the curve, for example, you know. But, or we could figure it out from basically rotating the gradient vector 90 degrees, you know. Like, for example, if this thing was 0, 2, and this point was 3, 4, then my tangent line could be parameterized by like gamma of t is 3, 4 plus t times, oh, I don't know, 1, 0. That is by no means unique, but there would be a tangent line which is perpendicular to the gradient. Yeah. Other questions? So the purpose of the level curve homework is to try to get you guys to like think about it for yourself, because I can talk about level curves all day in class, but unless you actually write some out and work with the idea, it won't become real to you. But it's not a complicated thing, actually, at all. All right. And the key thing to remember is that the gradient points perpendicular to the level curve, and it points towards the direction that you level up. Other questions? Okay, so the other thing that's in the homework somewhere, but I actually haven't talked about directly, is the concept of a differential. All right. So we can calculate the differential for a function of, you know, several variables. And I think at the moment, the best way to think about it is as a, let's say, formal expression. Calculus books tend to present the differential as a means for arranging an approximation of the function. That's not too bad, I suppose, but really, I don't think of it that way. I think of it as its own thing. And so here's what it is. And I'll just show you a few. If f is a mapping from, say, Rn to R, all right, and x1, x2, xn are, you know, variables for Rn, then the total differential of f is defined to be df equals to partial f, partial x1, dx1 plus partial f, partial x2, dx2 plus partial f, partial xn, dxn. There is sort of, well, let me just do a few of these, and then I'll talk more about how they can be interpreted. So I guess this was example 2. So example 3, suppose we had f of xy equal to, let's do x over x plus y, right? What's df equal to? I have to do these partial derivatives is the thing, right? So what is that? That's minus parentheses x plus y minus x divided by x plus y quantity squared. That's the quotient rule. And over here, I just get minus x over x plus y squared times dy. Of course, I can clean that up a little bit. I think the x's, they'd be canceling, so I've just got like basically minus y dx minus x dy divided by x plus y squared. We could write that kind of thing. That's allowed. So there you go. That's the total differential of the function. That's it. So the answer involves differentials. This is the nature of the total differential. What'd I do? Well, the second one only has a y in the bottom, so the x just rides along. I basically look at that as this differentiation basically is like x times 1 over u, you know? So I do x times, minus 1 over u squared times partial u partial y, but here u is x plus y. So my logic is that's minus x over u squared, which is what I wrote here.
I'm talking about
The first one, what did I do? Something wrong?
Is there a minus?
Oh man. Oh, yeah. Thank you. Which means, well, the x still cancels like it shouldn't have in my previous step, right? But we're left with a positive y. Now are we good? All right, cool. So this is the total differential, yeah? Let me just do another, yeah? Yep.
So we just leave the dx and dy argument.
That is part of the answer. That's how this works. Yep.
Thank you.
Example 4. If I had, like, what's the, let z equals to cosine of, theta squared plus beta squared. Calculate the total differential of this expression. Here we go. dz is minus sine of theta squared plus beta squared times 2 theta d theta minus the sine of theta squared plus beta squared 2 beta d beta. So I could factor out a minus 2 sine of theta squared plus beta squared, and then that would leave me a theta d theta plus beta d beta. And there you go. That would be the total differential of z. So like, if you're not following what I'm doing, I'm suggesting that in that context dz is partial z partial theta d theta plus partial z partial beta d beta. That's how that works. Since z is a function of theta and beta, that's the total differential. Would you like to see another? Let's do another. If I have w equal to xyz, then what's dw? I've got a x derivative of xyz dx plus a y derivative of xyz dy plus a z derivative of xyz dz. And so what I get, the total differential of my w is yz dx plus xz dy plus xy dz. And there you go. That is the total differential of w. Simple as that. So if you're, there's a couple different ways to look at this. One is that this is just a formal notation to keep track of a bunch of partial derivatives all at once. All right, let me repeat that. It's a formal notation to simultaneously present partial derivatives of several variables at once. Right? Like, for example, to make good on that comment, if I told you that dw was like Pac-Man dx plus Ghost dy plus SpongeBob dz, and then I asked you, what's partial w partial x equal to? what's partial w partial y equal to? And what's partial w partial z equals to? If you accept my program of formal notation, you can answer those questions respectively as Pac-Man, Ghost, and SpongeBob. Yes, very good. There we go. My SpongeBob sometimes gets deformed, but whatever. Now, of course, this all begs the question is, what on earth do you mean by dx and dy and dz, right? Well, I can give you different levels of answers to that question. The answer that I ultimately give in mathematics is that it's a one-form field. It's a mapping on vectors that spits out numbers at a point. It's a so-called dual vector. But that's not the answer I give here. The answer I give here is it's just a formal notation to gather together partial derivatives. And we could use it as an approximative procedure. Like, let me show you that. Like, suppose you've got a cube. Oh, not a cube. Let's suppose we got a sphere. Right? And I'll go back to the cube. Here we go. And suppose it's got, width x, depth y, height z, right? The volume is what? X, y, z, right? So if we take the differential of the volume, we've got dv is, well, we just worked it out, didn't we? So yz dx plus xz dy plus xy dz, right? So if x is equal to 10, y is equal to 20, z is equal to 30, and the uncertainty in x is known to be 1, the uncertainty in y is known to be about 3, and the uncertainty in z is known to be about, 5, what's the uncertainty in your measurement of the volume? Well, the differential basically gives you a guide. It says, well, the uncertainty in the volume is, roughly speaking, 20 times 30. My, delta x rather, which was 1, plus delta x, so 10, rather x times z was 10 times 30 times my delta y, which is 3, and then my x times y, which was 10 times 20 times my delta z, which was 5. All right? Yes, sir?
In this example, what does uncertainty mean?
Uncertainty means that I know that I've measured the length of the box, be 10, but I'm not really sure. It could be as little as 9 and as much as 11.
Okay.
So the uncertainty, right? Yeah. So like another way to express this might be x is equal to 10 plus or minus 1. All right? So my measurement of z is pretty rough, right?
Yeah.
But there you go. Like this would be the resulting uncertainty in the volume. The volume plus or minus that. So this is one of the main applications in terms of like if you want to use differentials for something. But you notice there's a distinction here, a significant one, which is I'm thinking of dv as an infinitesimal change in volume. Whereas here I'm actually thinking about a finite change in volume. But the infinitesimal guides the finite in this way. But anyway, that's one of the things you could use the differential for. But again, for us, the main purpose actually is what I revealed to you in example 6, truth be told. All right, well that's all I got to say about differentials for now. You guys have any other questions about stuff? If not, I'm going to return to previously scheduled programming and continue our work on understanding what the gradient looked like. Remember we were working out what's the gradient look like in polar coordinates? Yeah? So let's keep let's work on that. So I was suggesting an algebraic solution to solve for partial y and partial x, and we did the algebra to find partial y. And I'd mentioned that you could also use the chain rule, and now I'm going to go back and do the chain rule thing. So here we go. So we're working out the gradient in polar coordinates. All right, so what is partial theta partial x equal to? What is partial theta partial y equal to? Remember, this is partial x of inverse tangent of y over x. And here we got partial y of inverse tangent of y over x. We did these before. It's 1 over 1 plus y squared over x squared, right? But when we take the derivative of the inside function, it's a little different for x and y, right? For x, what's the derivative? Well, it's the reciprocal, right? X is in the denominator. So we end up with a minus y over x squared, right? But for this one, we just get what? The partial derivative with respect to y of y over x is just, well, 1 over x, right? Then a little bit of algebra here, but this gives us minus y over x squared plus y squared. And this gives us x over x squared plus y squared. So there's your partial derivatives of the polar angle. What we also will need in just a second here, so I'm just going to do the calculus while we're at it. What's partial r partial x equal to? We get what? We get 2x, right? Over twice the square root of x squared plus y squared, do we not? The 2's, they cancel out. What are we left with? Yeah, x over the square root of x squared plus y squared, right? And likewise, partial r partial y is equal to, same calculation almost, y divided by the square root of x squared plus y squared, right? Right. Can you guys tell me how to simplify any of these things in terms of polar coordinates? Like how can we reformulate these in terms of the polar coordinate formulas? Let's write those out, lest we have forgotten them. X equal to r cosine theta. Yeah. And y equals to r sine theta. Let's see here. What else do we know? Let's get it all out on the table here. Oh, okay. Very good. R is equal to the square root of x squared plus y squared. Theta is equal to the inverse tangent of y over x for x greater than 0, right? But it's, well, anyway, enough about that. And what else do we know? Let me also remind you that we have previously worked out r hat is cosine theta sine theta, right? And we also derived that theta hat was minus sine theta cosine theta, remember? We actually worked those out from normalizing the gradient of theta here. So those are the unit vectors that point in the direction of increasing r and theta respectively. All right, so now I'm finally got everything out in front of us. How does this simplify? This is what? It's okay, I got it. So we have, what, minus r sine theta upstairs divided by r squared, and this is r cos theta divided by r squared, right? So what's that work out to? Yeah, minus sine theta over r and cos theta over r, right? All right. And this is what? That's r cos theta over r. This is just cosine theta. And this is just sine theta. All right. So let me go back. I'm trying to figure out what is partial x in terms of polar coordinates. And the chain rule says that that's actually partial x, partial theta, plus partial theta partial y, partial, oh, my bad. I'm an idiot. We're expanding x in terms of the polar coordinates. So I usually put the r's first anyway. I've got theta on the brain. So partial x, partial r, and then partial theta, partial x, partial theta, right? But what are those? We just worked those out, right? Partial x is cos theta, partial r, right? Partial theta partial x is minus sine theta over r, right? Partial theta. On the other hand, if we calculate the y derivative, we've got partial y, partial r, plus partial theta partial y, partial theta. Which, if you use what we worked out just now, is sine theta partial r, right? Plus cosine theta over r, partial theta. And I think we derived, let me put a box around these. So we derived the second one of these last time, didn't we? But I used a really different approach. I solved, we had worked out what is partial r and partial theta, right? Remember last time we did similar calculations, and we learned that if we work out partial r in terms of x, what did last time we worked out partial r was, what was it? It was partial x, partial r, partial x, plus partial y, partial r, partial y, which of course is, x over the square root of x squared plus y squared, partial x, plus y divided by the square root of x squared plus y squared, partial y. I mean, I think that would be sort of the analog of this, and partial theta, on the other hand, works out to minus y over the square root of x squared plus y squared. Oh, my bad. Not that, but it's here. All right, so there we go. We got everything in front of us now. So this still doesn't answer the question, how do you write the gradient in terms of polar coordinates? Maybe you guys can help me figure it out, though. So let's start out with the gradient written in terms of, oh man. So you guys tell me, what is the gradient in terms of Cartesian coordinates? Right, we usually write it in like the angle bracket notation, right? But really we want to use the vector hat notation here for best results. So gradient of f we can rewrite as partial f partial x times x hat plus partial f partial y times y hat. So what is, what is this? Well, partial f partial x, as we just have worked out, is actually, cosine theta partial f partial r, right? Minus sine theta over r, right? Partial f partial theta. That times x hat, right? I'm going to leave some parentheses here. We'll put in what x hat is in a more clever way next. And then partial f partial y, well, you guys help me out. I can't read from here. It's sad but true. What is partial f partial y? You can kind of see it from here. Sine theta partial f partial r. You guys help me out. Was it plus cosine theta over r?
Yep.
Partial f partial theta. All right, great. So you guys, you tell me, how do we put x hat in terms of r hat and theta hat? How do you do that? How about this? X hat should be equal to x hat dot r hat times r hat plus x hat dot theta hat times theta hat. Because r hat and theta hat form a basis for the vectors, so any vector, in particular x hat, can be written as a linear combination of the r hat and theta hat directions. But you guys tell me, what is x hat dot r hat? Look at r hat, right there. X hat dot r hat is cosine theta. So you have cosine theta r hat. What's x hat dot theta? X hat dot theta hat is minus sine theta hat, right? And likewise, y hat we can write as y hat dot r hat plus y hat dot theta hat, and that would give me minus sine theta r hat plus cosine theta hat. Now what we're going to do is we're going to take those and we're going to replace x hat and y hat with the corresponding appropriate combinations of theta hat and company. All right, so this is going to give me x hat, remember, is cosine theta r hat minus sine theta hat. And this one is minus sine theta r hat plus cosine theta hat. So I'll put everything down here. There's an r hat, and then everything else from the theta hat. So how's that work out? So here's this guy, right? That gives me cosine theta partial f partial r. This is cosine squared theta, right? Minus sine theta cosine theta divided by r partial f partial theta. I see I made my parentheses woefully too small. Sorry. So that's just from this first term, all right? Then next I'll do this guy times the second factor, which is going to give me minus, oh man, what the what? Dudes. This was a plus. This is a plus. Y hat dot r hat is sine theta minus sine theta. You guys got to stop me. This is a plus. So plus sine times sine. So sine squared theta partial f partial r, and then plus sine theta cosine theta divided by r partial f partial theta. That was all the r hat term. Now for the theta hat term, I got myself a minus theta cosine theta divided by nothing. Divided by nothing. Partial f partial r. And then plus sine squared theta over r partial f partial theta. Now that, so far, let me, truth in advertising here, that one is from this piece. And then, from this one, plus your sine theta, cosine theta, partial f r, plus cosine squared theta over r, partial f partial theta, all with a theta hat over. And what do we get? Lots of stuff cancels here, right? So what we end up with is simply partial f partial r hat plus 1 over r partial f partial theta hat. Or if you like, we could write it this way. Nabla can be expressed as r hat times partial r plus theta hat times 1 over r partial theta. That's how to express the gradient operator in polar coordinates, just like that. Shall we take this out for a spin?
Yeah, let's do it.
Let's try it. Let's try this out. Let's calculate the gradient So let's calculate the gradient. What example am I on? I've lost track. 7? Oh, example 8 then. So suppose you have f of x comma y equal to, oh, I don't know, x squared plus y squared plus z squared to the 3/2. Oh, there's no z squared here. Where does z squared come from? Dudes. No. Times inverse tangent of y over x quantity squared. So if we calculate the gradient of f as partial f partial x comma partial f partial y equals sadness. Agree? Sadness. But if we look at this function in polar coordinates, this is nothing more than r cubed times theta squared. And so as I calculate the gradient of this in polar coordinates, I have partial r of r cubed theta squared r hat plus 1 over r partial theta of r cubed theta squared theta hat. This marker's dead. We seem to be out of black markers at the moment. It's really, all my black markers are dying and I can't replace them. So what's this work out to? Well, we've got 3 r squared theta squared r hat, and then plus 1 over r. Well, we can pull the r out, right? So that just gives me a what? These squish down to r squared, right? And then the theta gives me a 2 theta hat. And there you go. That's the gradient. And if you wanted to, you could convert that back to xy coordinates. What? Yeah?
In the box equation, over there, the second one, is that variance times must be r theta.
Oh, yes, yes, yes. Thank you. Most definitely. That is what we derived right there, right? So, yes, very much so. Can you guys tell me how to put this back in terms of Cartesian coordinates? I mean, this is a perfectly good answer. If you have a problem that has like a circular symmetry, working out the model for it and the equations for it in polar coordinates is a wise thing to do. Going back to xy coordinates is like not really smart, but I can show you how to do it. If I wanted to go back to xy coordinates, it looks like this. This is 3 times x squared plus y squared. That's inverse tangent of y over x quantity squared. And you know, here the context, I'm going to just make our context x greater than 0 so that I don't have to quibble over the different definitions of the angle in different places. What's r hat in terms of xy coordinates? Well, it's x divided by the square root of x squared plus y squared, comma, y divided by the square root of x squared plus y squared. That's specifically r hat in terms of Cartesian coordinates. And then you got your x squared plus y squared times twice the inverse tangent of y over x. And then your theta hat is minus y over the square root of x squared plus y squared, comma, x over the square root of x squared plus y squared. But kind of the whole point of this is not doing what I just did in red. And then if you add these together, that is what you would have got from doing the purple derivative up here explicitly, directly. But the formula I wrote in black in terms of r hat and theta hat actually gives us much more geometric insight, as we'll see later in the course, for specific integrals and things.
We could leave it like that, or are we going to have to transfer from Cartesian to polar?
Oh, if it's this kind of problem, if I say like, if the problem says calculate the gradient in polar coordinates, I want the answer in polar coordinates. Yeah. I'm merely doing this to show you that we can, but also we don't really want to. Yeah. Okay, so yay, now we can calculate the gradient in polar coordinates if we want. So then, what other coordinate systems do we know? 3 dimensions, right? Spherical, cylindrical. So can you guys tell me how to write the gradient for a 3-dimensional function in terms of the spherical coordinate frame? I'm going to I should have erased all that. Oh, that's going to hurt. That's going to hurt a lot for what I'm about to do. Well, you guys are going to have to help me out. I might be okay if I don't erase the other board. So this one I can do. This one we get for free. What are cylindrical coordinates? X equals to r cosine theta, y is equal to r sine theta, z is equal to z. So the gradient of f in 3 dimensions is x hat partial f partial x plus y hat partial f partial y plus z hat partial f partial z if we write it in this explicit vector notation. But we just worked out